Continuing on with our algorithm design discussions, I want to introduce a new tool to you, and that's the use of flowcharts. Simply put, flowcharts are a graphical way of presenting algorithms. Flowcharts will use various shapes to define the steps that we have to do along the way, and we'll have arrows connecting these steps that will tell us how we move from step to step. Now, the reason why I'm introducing flowcharts to you is sometimes it makes it easier to figure out the solution or easier to understand the algorithm because it is a little bit more visual and you can kind of move these pieces around all the different steps that we want until we get them locked in where we need to have them to solve the problem. As I mentioned, flowcharts are comprised of a whole bunch of different symbols, and while these symbols can change from field to field, there's a common set of symbols that you pretty much see no matter what field you're in terms of the flowchart design, and I want to cover some of those today. So we first have the Terminator, and this is kind of those terminal points of where you start your algorithm and where you end your algorithm or your flowchart. So typically they would be start or return zero or end, right? There are parts where once you hit that, you know your problem is coming to an end. The next one that I want to point out is the process symbol. And the process symbol is pretty much anything that you want to do, but there's no choice involved, there's no termination, you'll just move to the next process. And so that's typically represented as a rectangle. Another one that's really important that you see all the time is a decision or a choice symbol, and it's always in this diamond form. And inside the diamond, you would put some type of condition. So if x is equal to 5, we're going to go this direction, or if x is not equal to 5, we're going to go that direction. And we'll see that in practice in just a little bit. The next symbol that we'll be using quite a bit is the data symbol. And then the next one is stored data. So I'm bringing these up together because you might be curious, what's the difference between data and stored data? Well, data is typically stuff that we'll keep in memory, so our variables, to where stored data is things that we want to write to the hard disk, so our long-term storage, any file I/O, any database queries, that would be this symbol here for stored data, and our variables that we want to keep track during the running of our algorithm would be represented by the data symbol. So these symbols here kind of represent all the symbols that we're going to need for the bulk of the work that we do, especially within the data structures and algorithms videos. But again, you'll see some more as you go. Now, in order to piece all these things together, we'll use various arrows that will tell us how do we go from various terminators to processes to choice and how we use the data. Now, I'm only going to be focusing on, for the time being, on program control, program flowcharts in terms of what the algorithm should look like. There are flowcharts of how the user is going to interact with the system, how the database will interact. So there's a lot of other uses for flowcharts that I'm not going into at this point. So just keep that in mind as we go forward. Okay, so let's revisit the find max algorithm. We've seen it a few times, so we should be pretty confident in this algorithm and what we're doing. And now I want to show you what it might look like in a flowchart design. So first we need a starting location. So we're going to use the Terminator and we're going to call it start. And then we need to get our input in. So we know we're going to have data that is an unordered list L. And we know that we're going to have data that is N, which is the size of L. Well, if we remember how we were solving this problem, we were starting from the beginning of the list, going to the end of the list, and we're going to check if max, which we initially set to 0, is ever less than the location in the list that we're looking at. If so, we would then update max and continue on in the list. So we're going to need some variables to help us here. And so these are statements now. These are processes that we want to run, and we want to say I is equal to 0. Now, notice I didn't put this as data because we're not getting this in as input, right? This is something that we're going to do, something we need to implement into the algorithm. So I'm choosing to represent this as a process. And now we need to set max to be 0 as well. So now we've set up all the variables that we need. We're ready to start actually moving through the list and checking to see if max is less than L at I. So the first thing we need to do is see have we got to the end of the list yet. So as long as I is less than n, as long as that's true, we then want to check to see if max is less than the location in the list that we're at. Now, if that's true, we know that we found a new max, and so we want to update that max, and then we want to go to the next location in the list. So to go to the next location in the list, we need to increase I by 1. So we increase I by 1, and then we're going to go all the way back up to that decision point and see if I is less than n. If I is not less than n, we're going to go back into the loop, and we're going to check is max less than the next location, and if that's false, we'll skip down to just incrementing I. So we're going to skip over that max is equal to L at I, because L at I was not greater than max, because that decision point was false. And then we're going to go back up to the top decision point, and we're going to say, is I less than n? If that's true, we'll continue on and keep looping until we've exhausted all the elements in the list. And when that becomes false, we know that we found the max, and so we're going to return the value. So there's a couple things I want to point out here. Going from start to our end, which is at return max, there are no decisions that are left up to the reader. I know exactly where I should go at any given point, because the flow, the arrows, are showing me where to go. Once I finish this process, go to this process. And if you look at the decision points, once I go into that decision point and I identify if that decision is true or false, I know exactly which arrow to take from that decision point. So at any given point in this flowchart, I'm directed through the flow. Okay? One of the things that I like about flowcharts is it allows me to visually see what the code might look like. Because I see this loop here going from the I is equal to I plus 1 process all the way back up to I is less than n, I kind of see, oh, I might have a while loop here or a for loop, depending on what I need to use to implement it. And because I see at this decision here with max is less than L at I see an if else there, just because of the structure of the flowchart. So it allows me to kind of see what the code might end up looking like. And so when I go to develop this, I kind of already have an image of what the implementation might look like. But beyond that, which is more important, is it's easy to follow. It's clear. It's explicit. It's unambiguous. All the steps are laid out. The flow, the sequence is all laid out. So all those good things that we were talking about, what makes a good algorithm, apply to what makes a good flowchart. Unfortunately, there's not one presentation form to rule them all. You want to develop your skills with flowcharts and with more pseudocode style presentations of algorithms, because both of them have a place. And depending on the problem you're solving or the audience that you're communicating your algorithm to, a flowchart or more pseudocode natural language algorithm might be more appropriate. So the best thing you can do, especially early on, is develop both skills together, and they're going to help each other, right? As you perfect one skill, you're going to be perfecting the other skill. And you're just going to have more tools in your belt, so when a problem presents itself, you're ready to go.